All right, let's make a start. I'm very pleased to present the next speaker in the conference, James Reed from the University of Oxford, who will be talking to us about absolute representations in modern physics, followed up by Lorenzo with some comments.
Thanks so much, and thanks to Baptiste and to Chris for organising this wonderful conference. As you can see, this is based on joint work with Casper Jacobs. So we've learned a lot about the metaphysics or possible metaphysics associated, or possible metaphysics of space-time and reality over the last decade or so. We've learned that space and time might not exist at the fundamental level, and so on and so forth. What I want to do today is to continue to explore the metaphysics associated with our best theories of physics, but from a slightly different angle. And what I'm going to present an argument for, although eventually I'll not agree with it, is that certain objects that you encounter in contemporary physics invite a certain kind of perspectival realism. So I'll present that view and then I'll argue against it. I have a kind of side aim, which is to expose to philosophers of physics, all of you, philosophical literature which I don't think has received much attention from us. This is the literature on absolute representations. So I will start off by telling you a little bit about that, and then I'll tell you in more detail what I'm going to do in the talk. So here's Bernard Williams, super famous philosopher, but obviously not a philosopher of physics. He wrote an excoriating critique of Hilary Putnam's internal realism, which you can take to be a certain kind of internal perspectival realism as well. I won't go into it. He was saying that there should be an absolute conception of reality, rather than thinking that reality is fragmented or perspectival or whatever. This kind of line of argument has been taken up by my Oxford colleague and great Williams scholar, Adrian Moore. And in this book from 1997, Points of View, which I would recommend to all of you, he argues that absolute representations of the world from no point of view, I will tell you a bit more about what we can take that to mean in just a second, are possible, and that we should reject kind of perspectivalist way of thinking about the world. Moreover, Moore says that insofar as physicists might look at their theories and think that reality should be best understood through the lens of perspectival realism, they have more to do. Here's what he says about this. It's the business of physicists, as it's the business of no other inquirers, to find some minimal set of concepts that can be used for the indirect endorsement of any true representation. You should find some conception of the world which is consistent with everything, which is absolute in that sense, which doesn't rely on a certain perspective. Evidence that concepts that physicists currently employ are inadequate for these purposes is evidence that they have further work to do. Moore actually goes on to give an argument, a formal argument, quite abstract argument, that absolute representations are possible. But then we have a tension here, because on the one hand I was saying that certain kinds of objects which you encounter in physics invite kind of perspectivalism, but on the other hand we have these kind of very general abstract philosophical arguments that you shouldn't require perspectivalism. So how to reconcile those things? So here's the plan for the talk. This is actually the set of slides associated with an hour-long talk, so I'm going to skip some stuff. The first section is on absolute representations, what Moore means by this and what we can take it to mean. I'm just going to give you the highlights there. In the slides I do actually go through Moore's abstract argument, and I'm happy to talk about it, but I'll skip over that for the purposes of today's talk. I'll then present to you this mathematical distinction between geometric objects and non-geometric objects. And I'll present the case that non-geometric objects, which you do encounter in modern physics, general relativity, which is the case I'm going to focus on, but also theories of quantum gravity, very naturally imply some kind of perspectivalism. I'm going to focus in this talk on the case of pseudo-tensors, which is one kind of non-geometric object which comes up in general relativity, but what I say would apply to other non-geometric objects as well. And this is going to play out in quantum gravity as well, because think about your favorite theory of quantum gravity, maybe it's supersymmetric string theory. You have fermions there, represented by spinor fields. Spinor fields turn out to be non-geometric objects, so we're going to need to understand the metaphysics of those guys when we think about the metaphysics of quantum gravity as well. But the maths of spinors and that kind of stuff is, I haven't figured it out yet, whereas I feel I have a good grasp of the maths of pseudo-tensors, so I'll tell you about this case. So I'll present the case that pseudo-tensors as well invite perspectival realism, but then I'll use some more maths, stuff to do with forms on the bundle of linear frames. I'll explain what this means to show that in fact you don't need to go down this route. And that we can reconcile more in these arguments by saying in fact absolute representations, when I look at my physics and think about it in sufficient detail, are indeed possible, like Moore was arguing for. The maths which I introduced here solve some kind of other issues to do with pseudotensors, the so-called uniqueness problem. Again, I might skip that section, but we'll see. Okay, so Moore has a lot of terminology. He says a representation is anything which has content and which, because of its content, is either true or false. So any statement that's true or false could be, I'm here. That would count as a representation for him. I'm going to skip a lot of this. What I want to focus on, or what I want to draw your attention to, is what Moore means by a point of view. So he's trying to be super, super general in his book. And he says, by a point of view, I shall mean a location in the broadest possible sense. Hence, points of view include points in space, points in time, frames of reference, blah, 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 blah. We can focus on this case of frames of reference. So if we think about that, the idea would be we should be able to have a conception of reality which is liberated from reference to particular coordinate systems, particular frames of reference, which is not perspectival in that sense. There's a natural sense in which you can think about frames of reference coordinate systems as being perspectives, because they're kind of stand-ins for the points of view of certain idealized observers or something like that. Then the thought is, if we follow through with Moore's argument, it's an absolute representation, a representation from no point of view, a representation of the world liberated from coordinate systems which represent the perspectives of particular observers, should be possible. So Moore's argument to this effect is called the basic argument. This is the stuff I'm going to skip, but I'm happy to go through it. Let's just roll to the conclusion. Moore's conclusion is absolute representations are possible. And I think really that means like invariably possible. Like, however the world is, there should be an absolute representation of it, a representation liberated from points of view. But how does that square with the fact that certain objects seem to require points of view in a way that I'm going to go on to explain? So is Moore's conclusion, his conclusion of his abstract argument, consistent with what we know from modern physics? So now let me tell you a bit about the maths of geometric objects and non-geometric objects. I'm happy to take questions if people want any clarification about anything. So the formal idea of a geometric object goes back to work in the 50s by people like Nijenhuis and Schouten, later developed by Troutman. And the idea is that you start off with a manifold. Can I use this thing? I guess so.
Absolutely, yes.
So here's my manifold of points. Consider a point, and then consider the neighborhood of that point. I can lay down a coordinate system. But I could also lay down a different coordinate system. If I do something like that, then if I've got my special relativistic hat on, maybe I think that this is the coordinate system associated with an observer at rest going through this point P, and this is the coordinate system associated with someone moving uniformly with respect to that initial person, something like that. So you can consider a manifold, consider an arbitrary point, consider two arbitrary local coordinate systems around P. In order to specify a geometric object on M, you write down a set of components, a set of real numbers in each coordinate system, and a set of transformation rules relating the components in one to the components in the other. So think about like a vector. This is my vector. Sorry, this is should be bigger. I've got some vector v going through P. This will have a certain set of coordinates. So components in one coordinate system, it could be like 0, 1. It will have a set of components in some other coordinate system. It could be like 1 over root 2, 1, 1 or something. If I change my coordinate system. The numbers are different, but I have a well-defined transformation rule relating the coordinates in one to the coordinates in the other. And that allows me to kind of reconstruct what the object is. Think about the coordinates associated with the points of the corners of a cube, say. If I've got the numbers associated with all of these coordinates in one, with all of these points in one coordinate system, and a set of numbers associated with all of these points in some other coordinate system, maybe the one rotated by 90 degrees. If I was just given those numbers and I was given the rule relating the coordinate systems, I could extrapolate that I was dealing with a cube. So that's what we do to specify a geometric object. I tell you numbers associated with the object in different coordinate systems, and I give you a well-defined transformation rule relating the components in one coordinate system to the components in another. If the second thing is lacking, Nijenhuis dubs the associated thing just an object rather than geometric objects, but we'll call these non-geometric objects. What do we really mean by a well-defined transformation rule? This is nicely discussed in a recent paper by Patrick Durr, and the idea is that you should have some kind of transitivity or something like that for the components of the object in different coordinate systems. So if I start off with the components of my object in one coordinate system, and I transform to some other coordinate system, I should get the same thing as if I transform to that latter coordinate system via some intermediate coordinate system. Just shouldn't mess up by going through one route versus another route to get to the second coordinate system. So here are some examples of geometric objects: tensors, tensor densities, Christoffel symbols, and so on and so forth. So tensors are geometric objects. I give you components in one coordinate system, components in another, and I have a tensorial transformation rule, which features factors of the Jacobian matrix out the front, relating the coordinates in one system to the components in one coordinate system to the components in another coordinate system. Christoffel symbols don't transform tensorially, they pick up another term, but it's still a well-defined transformation rule. On the other hand, there are non-geometric objects aplenty which don't satisfy this conception of a well-defined transformation rule. These include pseudotensors, spinors, Yang-Mills connections, and other stuff. And it's quite easy to see in the case of a spinor. So remember, the spinors are ones where if you go around twice, you pick up a minus sign. So it's kind of like, my coordinate is 1 here, and then if I go around this, now it's -1. So I don't have that closure of the components which was required for a well-defined transformation rule. I'm going to focus on pseudotensors because I think these are slightly easier to grapple with and better understood. So what are pseudotensors? They're things which come up in particular in general relativity. They've been kicking about for a century or so, first written down by Einstein, Noether, Klein, Hilbert, and people like that. And the idea is that gravitational stress energy, or gravitational energy, the energy associated with the gravitational field in general relativity, is represented by a pseudotensor. And I have this conservation law for gravitation, or for total energy, which looks like this. And this is basically saying that the sum of the material energy associated with your material stuff like tables and chairs and electrons and so on, plus the gravitational energy, that whole sum should be conserved. This was first written down in 1918 to my knowledge. But lots of people have voiced lots of different concerns about those kinds of conservation laws in general relativity. So let me just pick up on 3 of the most widely discussed concerns. One is that, in fact, if you use the machinery of Noether's theorems, which relate symmetries to conserved quantities, well, because there are kind of infinitely many symmetries of GR given its diffeomorphism invariance, you have infinitely many conservation laws, and some people think that's weird. It would make sense to have one notion of gravitational stress energy, but how can I have infinitely many distinct ones? The second is that these conservation laws are closely associated to mathematical identities, and I think that's an interesting question, how far to take that concern seriously. Can mathematical identities have physical content? That has been discussed in a nice paper by Catherine Brading. The third is the one that I'm going to focus on. Gravitational stress energy pseudotensors are not geometric objects. They don't have well-defined transformation rules. Good. But what actually is the problem with non-geometric objects? It would be nice to be a bit more explicit about this. Sometimes in the literature, you'll find simply the assertion that we should just deal with geometric objects in physics. But can we kind of tease out the reasoning underlying that claim a bit more? So I think one way to do this is in terms of Klein's Erlangen program for geometry. And this is the idea that geometrical structures can be identified by way of specifying a set of transformation rules and thinking about the invariance associated with those transformations. So going back to the cube example, what's left invariant by my transformations of rotations and thinking about the components is just the abstract idea of a cube. And that's the way of kind of extracting invariant ontology from a set of components and transformation rules. Then the thought is that the objects that you identify via this Kleinian approach to geometry are going to coincide with things which are specified in a coordinate-independent manner. So in my example, just saying, there's a cube. So what I pick out via Klein's conception of geometry is ultimately going to coincide with what's picked out by an alternative approach to geometry known as Riemann's approach, which is all going in a coordinate-independent manner. And this is the stuff that our friends from Irvine like. So thereby, you can associate geometric objects with objects specified in a coordinate-independent manner, but not so for non-geometric objects. And here's what Pitts says about this. Thus, the components of a geometric object form a natural kind mathematically. They constitute faces of one and the same entity by virtue of being interrelated by a coordinate transformation rule. Kind of interestingly, Quine actually alludes to this back in the 60s at the end of his paper on natural kinds. So he suggests, although doesn't elaborate, on there being some connection between the notion of a natural kind, what we should really take your ontology to be, I guess, and what's picked out by the Kleinian approach. So he says, perhaps the branches of science could be revealingly classified by looking to the relative similarity notion that is appropriate to each. Such a plan is reminiscent of Felix Klein's Erlangen program in geometry, which involves characterizing the various branches of geometry by what transformations were immaterial to each. I won't expand on this. It's interesting to see that Quine was picking up on the same connection. So the fact that geometric objects have well-defined transformation rules makes them candidates, probably need to say more, but to be associated with natural kinds, like the real elements of your ontology, but not so for non-geometric objects. I talk about this a lot more in a whole paper, so I'll just refer you to that, but I'll leave it here. Okay, so let's zip over to pseudotensors in particular then. So there are obviously problems here with identifying an invariant ontology for pseudotensors, given that they're not geometric objects. So again, I'll just read what Pitt says on this. A pseudotensor shares with the Einstein tensor the physically interesting property of having a single recipe for inferring its components in the coordinate system from metric components and their partial derivatives. Ignore all that. However, there is no transformation rule that allows one to infer the components with respect to one coordinate system from the components in another, so there's no mathematical unity. So you can kind of see why you might take non-geometric objects thereby to motivate perspectivalism. I can understand what this object is in this coordinate system and this coordinate system, but the lack of transformation rules, the lack of well-defined transformation rules, means that I'm kind of struggling to extract a kind of invariant ontology liberated from reference to coordinate systems here. And so in turn you can see the tension between just the existence of non-geometric objects in modern physics and Moore's claim that absolute representation should be possible. So we need to figure out what's going on here. Good. So I think that we can address these issues, but we need to understand the mathematics of pseudotensors a little bit more. I think a lot of what follows will either be completely incomprehensible or juju to you, depending on who you are, but let me just go through it. So here's my manifold. Now I want to define what's called a frame bundle. So for every point of the manifold, I have a space, and this is the space of kind of all possible coordinate systems which I could lay down at that point. And I'm obviously going to have this for every point. So over here I also have a space of all possible coordinate systems associated with that point. Each of these spaces associated with each point is called a fiber. And then the frame bundle is basically the union of all of these fibers. So as Weatherall puts it, the frame bundle over a manifold, which you call L of M, is the bundle whose fibers at each point, P, consists in all ordered bases or frames for the tangent space. So all different coordinate systems that I can lay down at that point. So there's some jargon, but the idea is, I think, not that hard to understand. Now I can take what's known as a section of a frame bundle, and that's basically a choice of a particular coordinate system for this point, a particular way of laying down coordinate axes for this point, and so on and so forth. So a section of a frame bundle will give me basically one particular coordinate system on the original manifold. And depending upon the section that I take, we'll get different coordinate systems down here. So now here's an idea which was floated by Sabados, physicists who's done a lot of work on gravitational energy back in the early 90s. He wrote, if the geometric objects in the principle of general covariance were not required to be geometrical objects on the spacetime manifold M, but they were allowed to be geometric objects on the manifold of frames of spacetime, i.e. on the bundle of linear frames, this L of M, and if the previous coordinate and or gauge-dependent quantities and formulae like pseudotensors could be reformulated in terms of objects on L of M, then the contradiction with the principle of general covariance, by this he basically means the horrible transformation rules of pseudotensors, that problem would be resolved. So his ultimate idea is maybe I want to define stuff to do with gravitational stress energy, not down here to do with pseudotensors, but up here, and it might look nicer up here than down here. So we want to explore that. If this is like nonsensical to you, then I think the point is clear. I'll just put all the details down. So here's my frame bundle, L of M. I want to give it a basis, and I'll call the basis vectors the deltas, and I want to give you some one forms which contracted with those deltas, give the identity, and those I'll call sigmas. And then I can define this mathematical object, big sigma, which is just all of those one forms wedged together. It doesn't actually matter, I just need to tell you what this object is to write down some formulae on the next page. Now, whenever I have a fiber bundle, and I define a connection on that bundle, which is basically a way of moving from over here to over here when these P's and Q's are infinitesimally close, I can define what's known as torsion and curvature as well. These are the standard formulae for torsion and curvature. Again, we can go into what these mean, but it doesn't actually matter. The point is that having written down those objects, I can then define some things on L of M in terms of them. And the things which are going to be of interest to us are what are known as the Nestor-Witten form, which is called U, written U, and in particular this object which is known as the Sparling form, which is called little t. So the Nestor-Witten form is just defined as this guy, the spin connection wedged with that sigma that I had before. And the Nestor-Witten, the exterior derivative of the Nestor-Witten form is this guy, where I have the torsion and curvature occurring. But the point is that at the end I have this little t, which takes this form, and that's the Sparling form. The details don't matter. The significance of these guys is this. So basically consider any form t, big T, which satisfies this conservation condition. So this is a good candidate for representing material stress energy, because material stress energy satisfies a covariant conservation equation. Then I have the following theorem, which says if this spin connection is torsion-free, which you have in general relativity, then I have these two things. And this last thing is, again, looking like what I had before. I have some conservation of this big T representing material stress energy, and this little t. So this is kind of looking like it's playing the role that I wanted from gravitational stress energy. And I also have this other equation too, which I have an analog for in the case of the pseudotensors. So in the case of the pseudotensors, I have my material stress energy plus the pseudotensor being equal to the derivative of something. That U is called the superpotential in the standard non-frame bundle GR energy literature. And the point is that basically I have the same thing going, what looks structurally the same going on here as well. So I've defined this object, little t, on the bundle of linear frames, and it's looking like it's in some sense playing the right functional role for gravitational stress energy. Now obviously though, these are all living upstairs. How do they relate to stuff which is living on the base manifold? So let me answer that question, but just to flag, the heuristic to keep in mind is especially the second point. The Sparling form, which lives on the bundle of linear frames, is basically like a pseudotensor, but in the sense that it represents gravitational stress energy, but it's not actually a pseudotensor. It has nice transformation properties. So how do these things, these T's and U's which live on L of M, relate to pseudotensors which live downstairs? Well, as Salvador says, you can take various forms of the Nestor-Witten form and the Sparling form, and you can pull them back along local sections, yielding different superpotentials and pseudotensors. So what that means is basically choose a section, choose whatever section you like of the frame bundle, that fixes a coordinate system, and given that section, I can kind of move the guys living upstairs to downstairs, and I'll get different stuff living on the manifold again. And you can do this in different ways, and Salvador spends a lot of time proving this stuff. So if I pull back the Sparling form, then I get what's known as the Einstein pseudotensor. If I pull back a different version of the Sparling form, I get a different pseudotensor, which is known as the Landau-Lifshitz pseudotensor. Remember that pseudotensors are non-unique. That was one of the concerns that people had about pseudotensors. So these are like different candidate representation things to represent gravitational stress energy, different mathematical objects. But the point is that by pulling down T in different ways, I can get different pseudotensors. And I would claim that you can get all of them by choosing different sections. You have infinitely many choices of sections, and the choice of section that you choose will give you a different pseudotensor again, potentially infinitely many of them down on the base space. Okay, so I've defined some stuff on L of M. I've told you that those are geometric objects, not non-geometric objects. Now we need to think how this bears on that question of absolute representations. So I just want to introduce one further distinction, which is from Wallace. So he draws this distinction between something being coordinate independent versus coordinate free. So coordinate independent objects for Wallace are objects which might be defined with respect to some coordinate system, but not any particular one. You kind of need coordinate systems to define the object, but you don't need like that particular coordinate system, you just need some coordinate system. Versus an object which is coordinate free, which is an object not defined in terms of any coordinate system at all. So let's think about T and U then. So these are geometric objects on LM. They have well-defined transformation properties. They avoid the problematic coordinate dependence of pseudotensors. It seems that they're coordinate independent. Their definition doesn't depend on a particular choice of coordinate system, but just to flag that I think you can't really say that they're coordinate free, because they live on the space up here, which is the space of all possible coordinate systems. So you haven't like constructed a notion of energy which is completely liberated from coordinate systems, but you have constructed a notion of energy which doesn't depend on any particular one. So do these pose a problem from Moore's claim that absolute representations are possible? Well, they seem to satisfy his definition of absolute representations. So they're not from any particular point of view. They're not from any particular coordinate system. And he puts this definition in another way. Basically, you could take T and conjoin it with any pseudotensor you want and not get into a contradiction. So what in his terminology they're integrable by simple addition with any particular coordinate representation that you would choose. So they seem to satisfy his definition of absolute representations, which is good. Here's some concerns about what I've said. So one worry that you might have is that, well, I started off with a metaphysics of general relativity, which consisted of a manifold and a bunch of fields living on the manifold, in particular the metric field and material fields related by the Einstein equation. But by introducing all of this other stuff, haven't I just changed the metaphysical picture? So am I really doing the same? Have I really solved the issue or just moved to a different picture? But I don't think that this worry is actually a real concern. The point is that by specifying any differentiable manifold M, I get the bundle of linear frames for free. It's kind of, I don't know what Armstrong means by an ontological free lunch, but it seems like it is. So it's kind of like fixing M, I kind of uniquely get L of M anyway, so kind of already implicitly in my metaphysics. I think you could connect up with what Thomas Barrett has said recently about implicit definability and ontological commitments here. That's also the case for my T and for my U. So little t, little u can in fact also be defined given just the standard structure of general relativity. So as Pitts discusses in this article, if I write down the Einstein equation relating these guys on the base space, that's mathematically equivalent to that infinite list of pseudotensorial conservation laws, and that's something which has been shown and is known. But that again means that if I'm just doing general relativity, I'm thinking about metrics and material fields on a manifold, not only do I get L of M for free, but I get all of the pseudotensors, which are basically in turn associated with T, depending upon how you pull back T along different sections, again, for free. So I think the right thing to say here is it's actually only if you choose a particular choice of section of L of M, you say there's something special about choosing this section rather than that section, that you are introducing additional structure to general relativity. So it's only by choosing like one particular pseudotensor as somehow special that you're introducing additional structure. But if you just focus on what you get for free in general relativity, you get T for free. And that seems good. I think I'll skip this. So what does this T actually represent, though? What physically does it represent? Well, I think that the right thing to say here is just like a fairly straightforward thing. Well, it satisfies gravitational, it represents gravitational stress energy. It just turns out that it didn't live where you might have thought it lived. It didn't live on the manifold, it lived on the bundle of linear frames. It satisfies you might argue, all of the functional roles that you would want from gravitational stress energy. Again, like I said, choosing a particular pseudotensor might amount to treating with an object which doesn't emit of an absolute representation, but you can only choose a particular one by transcending the structure that you're given in general relativity, by insisting on the preferred frame. Okay. The uniqueness problem I won't go into in too much detail, but I think it's actually fairly obvious what I mean. So one of the worries that people have is that gravitational stress energy is somehow bad in general relativity because I have an infinitely long list of objects, all of these different pseudotensors, which could potentially represent it. But by thinking about all of these things as being different pullbacks of an object T, which lives upstairs, you just don't really have the uniqueness problem anymore. It's T, this unique object, which should represent gravitational stress energy. So, good. Okay, so all of that, like I say, is to do with non-geometric objects in general relativity, and in particular to do with pseudotensors in general relativity. In that particular case, by going through the mathematics of these things, I think we can convince ourselves that actually absolute representations of the thing which we took pseudotensors to be representing, namely gravitational stress energy, are possible in general relativity. And that squares up with Moore's argument that absolute representation should be possible. Of course, we would want to do this in other contexts as well, so it's just a particular case. When I look at spinors in string theory, well, spinors, like I said, are non-geometric objects, so I'd really want to go through the same story in the case of spinors and convince myself there that absolute representations of what we take spinors to be representing and fermions are also possible. That's a project for a future day, I guess. But I think these are the kind of things that we should engage with, like, do the mathematical objects which we use in modern physics, whether it's general relativity or quantum gravity or whatever, compel us to have certain views about the world, perspectivalist views, which we might not want to have? Well, we need to go through the details. So, just to sum up, I've told you about, I haven't presented, Moore's basic argument to the effect that absolute representations are always possible. I demonstrated the tension between this and the existence of pseudotensors and other non-geometric objects. But I've argued that in the case of pseudotensors, the tension can be mitigated quite substantially just by thinking about the Nestor-Witten form and the Sparling forms, which are defined on the bundle of linear frames. So, cool. Thanks all for listening.
Now we hear from Lorenzo Cocca for comments.
Yes, it seems to me that there are two main components of your talk. There is the question of, do we need pseudotensors to do physics, and what kind of thing in the world do they represent? Mm-hmm. The other part is the connection with representations and perspectivalism. Mm-hmm. So on the second point, I think the thing to discuss there is the assumption that both you and Moore have that the reference frame represents the perspective of the observer that is at rest in it. Mm-hmm. And I'm not convinced that that is the case. That the reference frame represents the perspective, maybe either it means that it represents what the observer sees, or how the world appears to them, or maybe what they think. And in either case, I'm not sure it works. So, if I know general relativity, it's not clear that I will think that just because the car has a certain velocity in the frame where I'm at rest, that I will believe that it has this velocity and disagree with you if you say that it does. I may believe that that's velocity in my frame, but you will agree with me. Mm-hmm. And it's not also clear that it represents how the world appears to me. Mm-hmm. I didn't look it up, this example. There's one in the book of modeling where he models the trajectory of two objects, not one object, but in two frames, and in one it is low down. But actually, if you see how it appears by looking at light rays and see an observer, maybe in one doesn't correlate. So it's not clear that it represents how the world appears. Okay, on the other question of pseudotensors. Ben, you mentioned that there are other contexts in which they might be needed, but it's not clear why we need the particular example you gave. So in the paper, you motivated by the need to have gravitational stress energy, to have gravitational energy. But it's not clear why we need to have that. And you motivated by saying, okay, intuitively, gravitational waves should transfer energy or something like that. But from what I saw in the literature, there doesn't seem to be an intuition which is universally shared, quite the opposite. And I guess if you just want to have energy conservation for the rest, non-gravitational energy, you already have that the stress energy tensor is divergenceless, like nabla that is 0. So you can recover kind of the usual facts about energy conservation. And then what you have seems to be an intuition. And it seems to be a bit weak. Bobby Fischer said that he didn't believe in psychology, he believed in good moves. And I don't believe in intuitions, I believe in good arguments, right? And finally, just one last point is, you say that, okay, but fine, if you assume the pseudo-tensor that doesn't commit us to anything new because we already can construct them from the reference frames or the tangent bundle and we already have that. I'm not sure, because this clearly refers to the mathematics. I'm not sure that it applies to what the mathematics represents. So if you follow an approach like Artsenius and Dor in the 2012 paper, Calculus as Geometry, they are substantivalist about tangent spaces and things like that. So it seems that it works in your direction. But I actually think you can nominalize general relativity, and there the tensor will correspond just to relations between points of the manifold, so that you are committed to nothing less than points of the manifold. I'm not sure how to nominalize your thing. So if there is not a strong argument why I should accept it, it seems that on grounds of economy, there is good reason not to accept it. Of course, it doesn't apply to spinors or whatever. I don't know about that.
Yeah. I mean, thanks. There's a lot of super helpful and good stuff there. So I'll go through them, and if I forget anything, just say. So first of all, what's the connection between reference frames and observers? Well, yeah, it's a good question. I mean, the way that we think about these things in special relativity is something like, here's some observer without world line, and given certain assumptions about conventionality of simultaneity, certain similarity choices, you can associate a coordinate system with that guy. So having written this down, I can tell you a given coordinate system, but it seems like there's something dodgy going on. Can you go the other way around and say why the coordinate system represents this observer or something? Fair enough, and I think that you can have stronger or weaker views about what it takes to represent an observer in a given physical theory. Comes back to, I guess, my question to Sam. Having said that, I think that pretty much everything I said in the talk, including the concerns, would still carry over. You might very reasonably have the view that a fundamental theory of physics shouldn't make reference to coordinate systems. And that's a concern which lingers and which we still need something like this machinery to evade. So I kind of basically agree with you on that point, that there is this kind of which people have jumped over, but I think the concerns still survive. So the next thing I think was about gravitational stress energy, pseudotensors. Do we need them? Well, here's one argument for taking pseudotensors seriously. So we, for a long time, had the view that there's an association between conserved quantities and symmetries. So this follows from Noether's theorems. So the theory is time translation invariant, has conservation of energy, and so on and so on. But there are infinitely many diffeomorphisms that you can do in general relativity, and each one of these chucks out a different conserved quantity if you grind the machinery of Noether's theorems. So that would be a prima facie argument rather than just intuition to take all of these guys seriously. Now, you might give other arguments to the contrary, but I would like to see those. And it seems to me that when people simply ignore pseudotensors, and by the way, I don't know, physicists often do use and talk about pseudotensors, and it's actually kind of, I don't know, I can't give a complete overview, but it seems to me it's kind of like philosophers who only like coordinate independent things, which are the ones that really repudiate them. So if you're insisting that whatever notion of energy that you have must be a coordinate independent thing, and maybe that's some kind of global notion like Bondi energy or whatever, then I think it's you who's making the additional assumption by saying that these guys are bad. don't know what you make of that, but that's really my initial reaction to that point. Sorry, can you remind me what your next point was?
The last one was about the ontological costs of
Right. Okay, so I have thoughts about that. Let me know what you think. So I would say that if I nominalize general relativity, haven't I just nominalized all of this anyways? Since all of this kind of you get for free from that. Looks like Alice.
Well, if you can recover them, so I'm not sure that to nominalize general relativity you need to reify the tangent spaces.
I see. Okay.
That's the
Right. Okay. So could you make sense of... So this avenue for understanding gravitational energy in that case would not be available to you, is that right?
That's what I'm worried about.
I see. But can you even make sense of the components of... These are non-rhetorical questions now. Can you even make sense of the components of an object, even a tensor, if you don't have tangent spaces? Because you need a basis for the tangent space to tell you what the components are, right?
Now you're raising a good point, because what you can do is, of course, to identify vectors to certain geodesics out of the point, or equivalence classes of those.
Right.
What you don't need to do is do the Artinius indoor, where every bundle is an extra space in which there are subtitles.
Yeah.
Maybe what you're telling me is that if I have like the just geodesics out of a point, and I can treat those as vectors, then I would be able to recover the pseudotensor and so on. Right, so I need to think about that.
I mean, I would love to... You've nominalized SR now, right? So you've nominalized SR, right?
Yes.
So are you working on doing general relativity?
Yes.
Cool. It would be great to talk about that. But yeah, thanks for the comments, they were really helpful.
All right, well, let's go to questions now. So please put up your hands. I'll take a list. And once I nod at you meaningfully, you can lower your hand. All right, let's start with Lucy. Everyone else keep your hands up, please.
I'm wondering what your opinions are on the relationship between mathematics and metaphysics. So we've looked at a lot of stuff about invariant mathematics. Do you think this directly represents what's going on metaphysically? You kind of mentioned it a little bit, but just maybe say a little bit more.
There's a few different things to say. So
Not a small question.
there are some people who might think that once you've written down the mathematics of your theory, you can just reasonably straightforwardly read off the metaphysics. For some reason I have David Wallace in mind, like just read off the ontology of a set of worlds of the mathematics of quantum mechanics. And I'm not sure I have quite that firm a view. I think that more interpretative work is necessary. So if I've got a bunch of maths, I need to make coherent physical sense of it. And maybe that's just a psychological exercise, but I need to know or have a good grasp in my head about what this corresponds to. There's this debate in the philosophy of symmetries, which is basically tracking the same thing, where interpretationalists, as they're known, this is a debate from Tom Muller-Nielsen, fall into the first camp, and motivationalists think that basically you need to do more interpretative work, fall into the second camp, and I would put myself in the second camp. Having said that, I think this is a spectrum, and on the one end you might have certain kind of primitive ontology people, for example, who think that the only way to understand the mathematics of a theory is in terms of point particles in Leibnizian spacetime or something like that. And I wouldn't go all the way down that end. I think there's some happy medium. That's where I would situate myself.
In particular about this stuff, so the kind of frame bundle construction, can you say a little bit about how to think about that metaphysically?
Yeah, I think this is a legit question. I struggle to kind of visualize it in a way, because all of my visualization proceeds from basically thinking about stuff in space-time, i.e. downstairs.
Yeah. Highly abstract.
So I don't know if I am being very compelling about what I find okay and what I don't find okay, but somehow I'm kind of unbothered by the, even if I can't visualize it, just because the L of m is defined in terms of the m, I think it's kind of like legit metaphysics.
Yeah.
I was wondering about this as well, and you know how this might be super naive, but you gave the example at the start of, you're looking at the positive square and then you realise it's a cube and the cube is the invariant description. I mean, is it the case that what happens when you add these, when you think of it in terms of these bundle spaces, that you end up thinking of just a higher dimensional object than a four-dimensional space-time?
I think, yeah, I mean, those guys definitely are higher dimensional spaces.
Yeah, and so maybe it's like looking at a four-dimensional object from multiple points of view in another dimension, in the same way that it's like looking at a square. Because I mean, it's got a similar feel. You're looking at the coordinate system, like at each point, you've got all of the coordinate systems. It's like looking at it from all different directions.
Yeah, it's good that you're talking about more. I kind of like, you start off with this as your like basic ontology, and it's just a four-dimensional manifold, stuff that we can visualize. And it turns out that you can like uniquely define other stuff from it. And guess stuff up here is kind of just like packaging stuff down here in different ways, because it's uniquely defined from stuff down here. So even if I can't tell you like a straight up story about what this guy is corresponding to down here, I think it's still kind of okay to talk about stuff down up here. But
I guess the thought was you might. Sorry, Lucy, you go.
Yes, the construction is still providing you with perspective independent metaphysics. Yeah, okay.
So think about, like, I don't know if this is an acceptable analogy or not, but again, in shape dynamics you have a bunch of three-dimensional snapshots of the universe, and you can define a preferred notion of time by like arranging the snapshots such that one is maximally similar to the next one and so on. And you could ask, like, what is that time? And I just say, well, it's something which is reducible to the set of snapshots. And I want to say roughly something similar here. I'm not. Have I addressed what you said, Sam? I'm not sure.
Oh, I mean, I guess I was just. I mean, I get that. Once you define the metric structure, then you get all the bundle formalism stuff in some sense for free. But that's kind of, and that's a mathematical fact about the structure you're using. But I mean, as you said, there's a question about how you interpret it metaphysically. And I get that. It's sort of coming out of the four-dimensional structure that you've got there, but you could still think of it as like looking at that structure from different angles or something.
I see. Yes. I mean, that's the sense in which it's coordinate independent, not coordinate free. But I guess Clasper and I, the claim that we're making is also that just given how Moore defines absolute representations, that's okay.
Uh-huh. I see.
It'd be even nicer if you could have a coordinate-free conception of gravitational stress energy. And some people like George Ellis have recently tried to do this, but I'm not sure if it works or not.
Okay. All right. Let's move on. So next, Baptiste.
All right. Thanks a lot to you and to Lorenzo. I think that's a very interesting discussion. I don't know how to put it. So I guess I agree with your claim that you show that it's possible to still have absolute representations if we are ready to help ourselves with fibers. But then I kind of wonder whether there is not. So is it the case that there is a kind of recipe that says the following thing? So look, you have some non-geometric object in your ontology. You don't like it. So let's just add some. Let's use the bundle formalism and add other spaces to bypass the non-geometric aspect of your primitive ontology. Then I wonder whether isn't it the case that you will you won't have a lot of time that you can really add as many spaces as you need to turn your non-geometric objects into geometric objects. And if that's the case, then I will have some kind of equivalence between two ways of looking at things.
Right.
So we'll basically show that it's very handy for us to geometrize the world, even when there is no geometry to bypass the thing. And I think that if you want to nominalize the bundles and try to avoid that, I guess, even though I agree with you that you show it's possible, it seems to me that would be a good argument to say that there are no absolute representations in the favorite picture, favorite way of analyzing things. Let me put it like, I think there is some kind of inclination to try to avoid reifying the fibers. And if you do that, maybe that may a bit undermine the motivation to say that everything is geometric in a way. I don't know, do you see what
I do, yeah. Well, I think it's, first of all, a good maths question, which is worthy of investigation. For any random, arbitrary, non-geometric object on the manifold, can you always understand it in terms of sections of some bundle? Yes. I don't know what the answer is, but I would like to know the answer. Yeah. And I would like to know the answer in particular in the case of spinors, which seem like the most important non-geometric object for us to look at. But I think even if you could, there would be the follow-on question of, is that bundle which you introduced something which is definable from the manifold, or is it something that you had to specify in addition? Because if you had to specify it in addition, as an additional piece of structure, then I think you would be guilty of the charge of just changing the question. The original question was, can I understand whatever my non-geometric object is supposed to be representing non-perspectively? And if I say, yeah, you can if you introduce this, if you have this extra piece of structure, well then, yeah, you're just like introducing more stuff to solve the problem. I think in that case, I didn't know if this is quite right, but then you would be more in down the line of like having to be a realist about this, having to reify it, a la Arrhenius and Dor. But if it's implicitly definable from stuff down here, like this one is, then it's kind of more okay. I think you don't actually have to think of this as like an extra piece of.
I mean, I guess there may be also set of. I wonder a bit like Lorenzo, even if it's if you can naturally build it, the fibers from the basal space. I mean, that's kind of a mathematical result, but it seems like you need a further assumption about the mathematics cracking reality in a transparent way or something like that.
Sure.
So I would need more. I would still be a bit worried, like if we are open to verify any mathematical space we can build from the basal space.
Mm-hmm.
I mean, I don't know, from a kind of from a naturalistic nominalist taste, it's a bit fishy, but I don't know. Even if you can have it for free. I mean, I'm suspicious about ontological free lunches in general.
Well, here I have in mind, for better or worse, I think you probably know much more about it than me, like Lewis-style functionalism. Like, if I can like define this thing for the stuff that I started off with, then that's good. I've done a functional reduction of that object. And
yeah, but I think it's fishy there as well.
Oh, you do? So it would be good to chat about that, because I like it,
yeah.
but I don't know much about it. But yeah, totally agree with the two maths questions. Can you always understand non-geometric objects as sections of a bundle, and are these bundles always implicitly definable from the original manifold? Good, excellent questions. Yeah.
Chris.
Thanks. So I'm very sympathetic to the Williams, Moore, Reed, and Jacobs kind of program of giving us an absolute conception of the world. I think this is an attractive program. I would like to note something, though, which leads to a worry I have, which goes in somewhat similar direction than as Baptiste meant. So that I would like to note sort of a dialectical asymmetry here, in the sense that the job of the absolutist in your research program is then to really show for each and every potential case of an entity that we need to somehow, in our representations, to show that some sort of absolute representation of that, absolute conception of that is possible. Whereas your opponent, it seems to me, it suffices that they show, here's one example where this does not work, and then the program is sunk, because then an absolute conception of the world is not possible.
Right.
And that makes me worry then, that the program is very vulnerable if you could show that somehow a similar move is not going to be possible for spinners or for Young-Mills connections or for other things you might think are necessary in our representation of the world. And I know you said this is further work and you maybe don't have, but I would like to invite you to say anything you can possibly to give us some assurance that maybe there is hope, or
Yeah,
reason to think this will succeed?
I'm optimistic, but
So
the more I
what's
read
the
about-
basis for your optimism then? That's my question.
the maths literature about spinors appears to be structurally similar to the maths literature about pseudotensors, where people talk about these guys, spinors, as sections of some spin bundle, whatever, and define objects on the spin bundle in the same way. But then at some point, I start feeling sick from looking at too much maths.
Okay, so that's reason for hope in the case of spinners, perhaps. But what about Young-Mills connection?
Sure.
Or, what is there a sort of an inductive argument?
Well, yeah, okay, so point one about the Yang-Mills connection, it is a geometric object on the bundle again. It's just not a geometric object on the base space, so
That should work.
that should be fine as well.
Yes,
And I guess
right.
if you really trust the thing which I skipped in the talk, namely Moore's abstract argument that absolute representations are possible, then you wouldn't need to look at particular cases anymore. You'd just be like, well, Moore's shown us that whatever you're looking at, you're going to have an absolute representation of it. But then it becomes kind of like your usual modus ponens, modus tollens thing, where someone's like, oh, I've got this counterexample, and Moore's like, well, it's not a counterexample because I've given you this argument, and they're like, well, tell me what's wrong with it.
Okay, thank you.
Yes.
Yeah, I'm also about the result, by the way, very interesting, and also it's what to come. And I'm wondering also about the question about how much there's extra structure in this picture. A different thing one could say. So, for instance, how do you connect these different fibers? I mean, when you take the sections, do you restrict to, say, certain kind of sections, or do you allow for any kind of section?
You could take any section you want, but my claim was that by choosing a section, you are introducing additional structure, because you're saying this section is privileged, and it's basically like choosing a preferred frame.
Ah, okay.
But if you don't, I mean, in GR, no one's told you that this frame is better than that one, so you don't have a privileged section. You can take any one you want, but no one's told you that that's a good section.
Yeah, that's true, but even, I mean, so you're kind of free to choose sections as you want, but aren't there perhaps some sections you couldn't choose to begin with because they don't really link up coordinates systems in some continuous manner or so? I don't know. I mean, is there any restriction like this which you could
think
of?
The section should always give you a smooth frame field, right? Isn't it like the sections of a Yang-Mills bundle?
I don't know. So I'm just wondering. Yeah. Okay. I see.
I think. I mean, I should check, but if it were to, you'd have to have something like weird about the section, or it's like discontinuous or something to get something horrible going on down here.
Okay, good. And then something slightly different about Noether's theorem. So is there a way to lift up also the symmetries into this other space?
Can you just say a bit more about?
I mean, so far you have, so to speak, then the symmetries on the manifold level, right? Because there's still spacetime symmetries, and you have the conservation laws at the level of the LM structure, the fiber structure. But I mean, I don't know, in this literature, do the symmetries also exist in some lifted form, so that you kind of express them as transformation rules at the level of LMM or something like this?
Yeah, that's an excellent question. Is this the acceptable way to read? So you could do like a diffeomorphism on the base space. And
yeah.
What does that?
I think even the question, what does it induce, so to speak, in other space? And yeah, I'm just widely wondering whether, yeah, I don't know, just wondering. But, and then the last thing is just about the superpotential. So is there anything special for the superpotentials? As you were mentioning them, he has an issue than just them usually. I mean, the same issue like always, right? That you can have superpotentials to conserve charges in principle, right? There was nothing specific here.
No, it's like your usual superpotential.
Yeah,
you'll
okay,
get out
yeah.
of the second theorem, but
Yeah.
just in this particular case.
Yeah.
Okay.
Yeah. No.
Yeah, there's one thing. It's a different bundle theoretic structure, but one way that people cash out, if the people who like bundles sometimes talk about non-geometric objects and geometric objects in the language of natural bundles as well, which is something that Nijenhuis went on to do in the 1970s. And there the idea is that a diffeomorphism of the base manifolds doesn't lift to a diffeomorphism of the internal space of values if you've got a non-geometric, non-natural bundle, which kind of makes sense because like what you do down here doesn't like uniquely nicely determine what happens in the space of coordinate values of this object. But that's a slightly different question to the one that you're asking, which is how do the symmetries of M relate to the symmetries of L M?
Yeah, okay, but this is also good. Yeah. So that's it for the moment.
Yeah. So, I mean, I have a lot of sympathy with this, but trying to kind of play devil's advocate for a minute. One thing, I guess this is kind of maybe a way of glossing some of the unease that's been expressed so far. There's a certain kind of sense in which it feels like a kind of brute force procedure, this kind of more inspired construction of the absolute objects out of a set of perspectival facts. And the kind of the fact that you can always do it might be kind of taken to be worrisome. Even if one can always kind of recover the tangent space facts from a manifold, there's a kind of further question you might ask about kind of which is the more natural or fundamental, kind of metaphysically natural or metaphysically fundamental kind of description. And you might think that kind of, if you're a kind of perspectivalist, you're going to think, well, of course you can kind of by brute force kind of take all the facts from all the perspectives and mush them all together into one thing. But what you'll end up with is a lot less natural than the perspectival description in the first place. And so you kind of be moving away from something that captures the true fundamental reality. So even if you can, I guess the simple way of putting the question would be, even if you can always construct these absolute descriptions, do we automatically have reason to think that that's like the fundamental description? It might be absolute but less fundamental than the non-absolute.
Yeah. So on the question about whether this is always possible, just to say that my intuition is that it is not always possible, because there's something super special about LM. It's like one of the few bundles that you can define from M, but I don't think any random non-geometric object is going to be best understood as a section of LM. That was something which was special to.
But the more argument is supposed to be general to any
so I think
description.
So I guess I just don't know what to say about those other cases. If you really like more, there's got to be some way of giving the answer, but I'm not sure it's going to be LM.
Okay, so it is something specifically about the way this procedure is implemented with respect to LM that goes beyond the availability of the description to make one think that it's a fundamental one. And it's the recoverability you've stressed doesn't seem to me to quite fit the bill there, because even you can recover often a derivative description from a fundamental description. But it doesn't mean that the fundamental one isn't more fundamental than it. So, like, you can imagine a perspectivalist insisting that this construction procedure you've described is kind of moves in the direction of absolutism, but also in the direction of derivativeness at the very same time.
Yeah.
And it actually kind of proves their point.
Okay, so can I just say this is a slide I skipped over. So we've got the Sparling form defined on LM, and this is mathematically equivalent, given the availability of an infinity of different sections, to an object which Pitts constructs via what's increasingly becoming known as the process of Pittsification, which is take the components. I've got my pseudotensors, and they're non-geometric objects, but Pitts says, turn it into a geometric object in the following fairly straightforward way. Say, in this coordinate system, these are the components, in this coordinate system, these are the components, in this. And that Pittsified object is a geometric object. But that's not what, well, I hope it's not. This is mathematically equivalent to the Sparling form defined on the bundle of linear frames, but, I mean, I don't know if I can consistently defend this. It seems to me that the Sparling form is different from that Pittsified object. You actually had to do some quite hard work to construct the Sparling form.
Yeah.
But maybe you don't share.
Are there more questions?
There are, yeah.
Cool.
But we've got a bit of time.
Yeah, I mean, this is kind of coming to what I was kind of thinking about when I was kind of staring at this. It's a quite obscure way that it's a kind of deep-looking argument, but it presents in a somewhat obscure-looking way.
That chapter is profoundly confusing, because his process of writing down the argument is he tries one thing and then says it doesn't work and then tries something else, and at the end you just have no real idea what the argument is. And Casper and I have tried quite hard to extract what we take the form of the argument to be, and we sent it to Moore and he said, yes, that is correct, but I don't know why he didn't write it like that.
Yeah, I don't have it here now, but the here it is. It's kind of, he says it's the the way in which can't find it now.
I mean, I
It
think
seems like the kind of the way in which you get your geometric object from a non-geometric object, there might be more or less kind of naturalness attaching to those ways.
Mhm.
And what I took you to be thinking is that kind of what you talked about is more natural than
Yes.
the pizzification way, even if
Right.
you kind of get to the. But then, kind of in general, you know, even if this way is more natural, it might still not be kind of as natural as just kind of staying where you started and extracting the perspectivalism.
True.
And I think a kind of
Yes.
dedicated perspectivalist can probably kind of try to push that line.
yeah.
You can do it if you like, but what you've got is a kind of slightly less artificial version
Mm.
of this like generally artificial procedure.
Yeah,
Less
so-
artificial than pizzification, but it's still artificial.
So I think there's several questions. One is like, are these two things, T versus the pizzified object, actually distinct given that they're or in what sense are they distinct given that they're mathematically interdefinable? And another is, just grant that they are distinct in some sense or other, which is more natural, and I think that that requires argument one way or the other.
Yeah. It's what I was looking for was the account that reveals how,
Uh-huh.
and those like ways of ways that the account could reveal how this works might be different in the different cases and look much more natural in
Mm-hmm.
some of those. And that's something we need to kind of assess for naturalness, not just the descriptions
Right.
themselves.
I actually completely agree with you, yeah.
Chris, you had a figure on this.
Yeah, I think actually much of my point has already gone over as my follow-up. If I don't know exactly what Moore's argument's supposed
I mean,
to
I could
be,
put
but
it-
is it not just that it's you can integrate these perspectives into some sort of totality in some sense, and that seems some sort of in some way an operation that's always possible. So you can always get to sort of a non-perspectival absolute conception.
Right,
like that.
it works
And-
exactly like that, yeah. So,
and
sorry.
and just to finish that, and then it seems to me that pizzification, even though it may be somewhat unnatural, is a form of integrating like that, pretty straightforwardly. Or,
Yeah, so here's how Moore's argument works. I think that you pretty much put it, the core of it right, that suppose you have two incompatible perspectives, like the representation of an object from one spatial perspective versus another one. These can't be integrated by simple addition, i.e. by just like conjoining them. But there'll be some other representation which reveals how both of these are true, and for more that won't be any kind of, from any particular spatial point of view. And then keep running the argument for like temporal points of view or whatever, and eventually you'll arrive at something from no point of view. Now, but there does seem to be a conceptual distinction between something being from no point of view versus being from like the union of all points of view.
Every point of view.
Yeah.
Once, yeah.
Yeah. And
but then I'm worried that Moore's argument only really leads us to the point where we have some sort of the totality of all points of views rather than no point of view, if there is some difference between them. I would need another argument to get to the latter.
yeah, I think that Moore would probably be able to respond to you, but this is where his book gets kind of
Okay.
delicate. I think he's going to have somewhere something like any representation is from one particular point of view, and so you can't just combine, say, the spatial representation of this object in that point of view versus that point of view by saying it's like has these by doing the pizzified move, because that's not one point of view; it's like the sum of two of them, or something. And you want a representation from anyway. But then how would Moore justify that question? I don't know. I need to look at this book again. But yeah, I completely agree that we need to be clearer about why representations from all points of view are not okay for Moore. And actually, I don't know if I put the quote, Moore does say, he does engage with this somewhere, and he's just like, this is obviously not what I'm after, and then moves on.
He talks not about like appending all the points of view together, but appending the different ways in which the account shows how you get kind of the perspective on reality from reality. is a kind of higher level thing, that kind of like the grounding principles or something that are involved. So I guess it was those sorts of things I was thinking could be assessed for simplicity.
Yeah, let's move on from more scholarship for the time being. Nick.
Yeah, well, I think kind of a good part of my question just got sort of brought out more clearly kind of here, but that seems right to me. There's what maybe what possibly right what Moore's after and what the argument actually shows. And of course it's clear, you know, but maybe in this case you can do better than, in some sense, better than pizzification, but maybe what the argument shows is that's what there must be or something. I think that's kind of plausible.
If his argument showed that a pizzified object is always possible, I would find that very underwhelming.
Yeah. Yeah. Okay, but I did have sort of there was sort of a flip side to that way of approaching it, which was, I mean, you had the slide up before that says Ti is equivalent to the
That was just a heuristic, just to keep in your mind.
Yeah, but that's okay, but there's a difference though, right? Because I mean, it's infinite, you'd have to say infinitely many, you'd have to give infinitely many of these objects. But in the pizzified way, you can actually say what it is, otherwise you're just saying there's some Ti right up there. So the question is, in what sense do you actually have a representation if you don't? You've got to have someone. Right? And one way of thinking about having a representation is I have to actually communicate to someone, you know, or I have to be able to pick out, you know, which one it is. Like what the tensor. I mean, it's sort of a thing I have with, I think, with coordinate-free objects in general. Right. I mean, the way I know to tell you what the object is in general is to actually go to some coordinates and write down the tensor in components.
Mm-hmm.
So you've given us this, but do we actually have a representation?
Right. I mean, though I'm not the which one it is question. Would that persist if you're considering the Sparling form? There's just one of them, and it lives on LM, and it represents gravitational stress energy. That's the line that I was pushing. And of course, I can give it components in a coordinate system, but I coordinatize LM, not M.
So maybe I'm not understanding the Sparling form. I mean, so the particular Sparling form is determined by the manifold?
Yeah. Well, no, sorry. L of M is determined by the manifold.
Yeah.
If I write on the manifold a metric and material fields which are related by the Einstein equation, then I can write down, so I'm working in GR rather than just with some random differentiable manifold. Then I can write down on L of M, T and U, and these are unique objects. And then my infinity of pseudotensors is associated with the infinity of ways of taking sections of LM.
So that's how you pick out the Ti by saying this is the metric and this is...
Yeah.
I mean, I guess my question arises at that level then, right? I mean, how do you tell me what the metric and the matter fields are without going to coordinates?
But that's fine. I mean, those are geometric objects on the manifold. So I guess the point is take a model of general relativity, which involves specifying a G and a set of material fields depending upon your interests. I guess part of the point here is that you get a lot of other stuff that you might not have initially thought about by specifying those things in your set of dynamical.
So then it is what is that? But that's an okay way to sort of give an absolute representation. Is pick some coordinates, tell you what the metric is, and then tell you the transformation law.
But I didn't have to tell you. I didn't have to pick any coordinates. I could be like full Irvine and just give you some angle brackets of M, G, and phi.
Yeah, but I guess that's what I'm being a bit skeptical about. But which metric is it?
I mean, I think I might not be following. Just like a metric fields defined on the manifold.
Right, but if I have the manifold, right, I've got R4.
Right.
There are infinitely many metrics.
Sure.
Which one?
I think, yeah, sure, there are infinitely many metrics, but the point, you have to choose, you've got your space of dynamical possibilities of general relativity, and each point in the space corresponds to a specification of the manifold and a metric, one of them, and a set of material fields. Precisely specified. Then you're just working with one metric on the manifold, and then the point is that having specified that one metric, you can define objects on LM.
But how did the specification get done?
That's just, I mean, that would depend upon your interests, right? I guess, you know, a theory comes with a space of dynamical possibilities, and you might select this dynamical possibility to represent this physical scenario. So I might choose like a vacuum sparse field solution of general relativity to represent whatever black hole.
But how do you tell me which solution it is?
I guess I'm saying that let's just roll with the idea that each model of a theory represents a possible world. Then
Yeah, I guess that's the bit I'm kind of pushing back on. It seems like, I mean, I don't quite know where this sort of enters into the argument,
but I'm not quite tracking the problem. I guess I'm saying, assuming the world is like this, i.e. as described by this model, then you have certain extra ontology.
But it's this model, right? I don't think you've done anything to justify being able to say this model rather than sort of some model. Right, I'm going to write m comma g mu nu, right? In this,
Yeah.
But that's, I can write every solution that way.
Sure, but that's fine.
But I haven't represented the particular geometry of a world until I tell you what the particular metric is.
Yeah, but that's completely agreeable to me. Like, this world is represented by this model. This model has such and such mathematical objects. From those mathematical objects, you can define other ones. I guess I'm not tracking the problem.
Which one of the infinite number of models is it?
Doesn't matter. Like, any model has an associated uniquely defined LM and associated uniquely defined Sparling form, and those will differ from model to model. But in any model of general relativity which represents a possible world, you will have a bundle of linear frames and a Sparling form. And the Sparling form will represent gravitational stress energy in that world.
So, but I'll try one more time. But I'm not worried about the pseudo-tensor part. Right? My worry is entirely at telling me which metric it is.
But that's just like, that's not something unique to my talk, right? That's like, how do I select a piece of mathematics, a solution of a theory, to represent a certain possibility? Maybe the actual world may be something else.
Right.
So that's like a very general question.
Right.
Yeah, and get into questions like general questions about representation.
It's actually not a question about representation, it's all on the mathematical side.
Mm-hmm.
I want to know which of the many sort of, mathematical metrics is the one you're singling out as doing the representing of a world.
I mean,
Is it the Minkowski metric, or is it some, the metric for some other space?
Well, suppose we look in the actual world and we think that the universe is expanding and there are black holes and so on. So if someone told me represent the world with a Minkowski metric, I would say you're mad. Like, don't do that. So there are some.
Right. So the Minkowski one, that's one I don't have to go to coordinates to tell you what it is. But for most metrics, to tell you which metric I'm actually interested in, I think I'd have to go to coordinates and write down a function in those coordinates.
I'm not sure I agree. I think you can specify metrics in a coordinate-independent way.
And you can differentiate them in a coordinate-independent way?
Two metrics, you might say are mathematic or distinct just in case one isn't related to another by diffeomorphism.
Right, that distinguishes them, but I want you to individuate. I want you to, tell me which one you are referring to.
I get, but they're distinct mathematical objects, right? So.
Yeah. But to represent it, okay. I mean, I'm trying to build more into representing, I think, than there being some sort of correspondence where you actually have to communicate to somebody else which representation you're interested in.
I do agree that things that
So I kind of want to know, well, what is the geometry of the world, right? It's not going to be enough to say, well, there's some g mu nu that does that, right? So you're actually going to have to write down go to coordinates and write down a matrix that sort of tells me.
Yes. So I mean, I think I agree in at least the following sense. So you shouldn't just think that models are in one-to-one correspondence with worlds. Like, consider a set of possible worlds related by some physical correlate of the whole diffeomorphism, and consider a set of models of general relativity related by the whole diffeomorphism. Like, this is one of the morals that's come out of the recent literature on the whole argument, that you could choose any of those models to represent any of those worlds. And you have to make this choice about, I'm going to choose this model to represent that world. And having made that choice, i.e. having fixed a representational context, you know that the other ones represent different stuff. But you could have made a different choice to start off with. So there is some flexibility in like choosing models to represent worlds in that sense. But I think there's some limits to it. Like, it would obviously not be a good idea, like I said, to represent the actual world or some expanding universe or whatever with a Minkowski metric.
Okay. All right, yeah, maybe I'll ask some more. Just to give some kind of context, this wasn't just totally random. And I think what I was trying to get at was the same sort of point about whether coordinate-free or coordinate-independent was tracking absolute kind of in the right way, and what it means,
Yeah, okay.
Right.
Yeah, fair enough.
That's okay. That was yeah.
I wanted to ask a question about the relationship between the thing you get up on the bundle space and the thing that you get in the ordinary base manifold. So, I mean, the thing that you started with didn't obey these transformations that you wanted, right? So that gravitational energy doesn't obey these transformations, and then you find some mathematics in here, and you find a thing that does.
Mm-hmm.
And now I want to know is like, why think that the thing you found is the thing that it is gravitational stress energy rather than some other beast that you found?
I think that the way to go there is like via some functionalist criteria. So you have a list of stuff that you think gravitational stress energy should do, like obey a conservation law with material stress energy, and like that little t satisfies that.
I see. Is it?
Because otherwise it's just like a random piece of maths again. Like, you need to show that actually.
Yeah. So in fact, the thing that fails. So the thing you started with by those lights isn't even playing the functional role of gravitational stress energy because it doesn't obey the right transformation.
I mean, that might be one functional criteria. I mean, it satisfies other ones, like it obeys a conservation law.
Yeah.
But you might also want, you might have other criteria, and at least the little t, the Sparling form, seems to be doing like a better job with respect to these criteria.
Right. So, but that other thing is still there.
Well.
So it looks like we've still got like two things, and one of them is doing a better job at satisfying the functional role for gravitational stress energy, but then you've still got this other thing that's not doing as good a role, and so like. I'm just sort of curious about what the relationship between the two things are, given that they're different.
I mean, the way that I'm thinking about it is you started off thinking about pseudotensors on the manifold, and how they have weird transformation properties.
Yeah.
Then you realize that pseudotensors are associated with sections of LM and pullbacks of T along those sections.
Yeah.
But in general relativity, no section is preferred. Or like, no one's told you that this is the right section, that's the wrong section. So really, you shouldn't be working with a particular section.
I see.
So, I mean, you can talk about pseudotensors if you want, but only by, in some sense, introducing extra structure.
Yeah.
And what I can define, just given the structure of general relativity, is something up here, which in fact turns out to be functionally nicer anyway.
Yeah. So the sort of thing that turns out to be a better satisfier for the functional role of gravitational stress energy is this thing up in the bundle space, not something that's in the manifold, although you think that's sort of packaged inside the manifold.
I mean, that's why I claim that I think it requires argument. Like, you might also think that some important functional role of energy is having some like causal efficacy, and I have yet to show you that little t has any causal efficacy.
Sure. Yeah, cool. Thanks. Lorenzo.
Yes. So as I said, I really don't know whether you can nominalize the part of Lm from a nominalistic theory about m. I'm starting to think that you can, but there's another objection that the maestro arbitrary field gives against using coordinate systems, coordinate frames, even those you can nominalize as aggregate of vectors. And the idea is one about intrinsicality. So if gravitational energy existed in the world, it seems implausible to assume that it either is caused or is metaphysically dependent on the properties of some vectors stemming or some curves stemming out of this point. This is the intuition why we shouldn't define gravitational energy in terms of these things, which are causally metaphysically irrelevant a priori. What do you think about this intuition?
I kind of agree with it, yeah. But that's I mean, would that apply to objects defined on LM as well? I mean,
well, it seems to me that it might still, why does this bundle? We are assuming that we can reduce everything we say about Lm to what we say about curves stemming out of points and the aggregate of those, which are the basis, like possible basis. So it seems that before we knew the theory, we thought that what they do is completely irrelevant to what the energy of anything is, a gravitational wave emitted very, very far away. And now we're saying actually that this property is constituted by some relations with those. So is that a defect of the theory? Is that something, or something you just accept, or we need to accept on balance? What do you think about this?
I'm not quite sure what to think. I mean, I think one question is, would Hartree-Field like coordinate independent, in Wallace's terminology, objects, or would he only be happy with coordinate-free ones?
That's an argument for coordinate-free ones.
Right. I mean, one thing, I don't know if this works or not, is you could say, yeah, I can associate what's going on up here with certain coordinate frames, which will in turn be associated with like world lines of idealized observers by pulling back stuff up here along sections. But in some sense, you don't have to. You can make that connection between the stuff that field doesn't like and the stuff up here, but maybe you just like don't do that. But I don't know if this is like too cheap.
Then we refine the bundles again, like extra space, and we say just as real. And
yeah, sorry, I'm not sure I have a great answer to this one.
Alright, we've got final short question from Elena.
Very short historical question. I was just wondering whether or why you don't refer at all to James Anderson program in the 70s, which was one of the points from which Pitt started, and he's discussing that it's probably you assume that Pitt has answered everything in this respect. Or
I think these are two very closely related but distinct debates. So one is about the nature of geometric versus non-geometric objects, which is a question about how things transform. But there's a separate debate about absolute and dynamical objects, and you could these things are orthogonal. So you could have a geometric absolute object, and that would be like Minkowski spacetime. Just sits there, not doing anything. It's absolute in that sense. It doesn't have dynamical equations, but it's still a geometric object. It's still a tensor. You could, yeah, and then you can cut the distinctions the other way. You could fill all of the 4 boxes if you wanted to. So I just think they're two separate questions. Like you point to an object, and one question is it absolute? And some people don't like absolute objects because they think that they violate the action-reaction principle, or they're somehow metaphysically problematic. And then there's whole debates to be had about whether you want to liberate your theory from absolute objects, and some people take that to be the moral of general relativity. But then you get onto like the questions about whether general relativity really has absolute objects or not. But I just view that as being kind of separate to the question about whether you should like non-geometric objects. Anyway, that's how I see things. We don't know that.
and you think that Pitts is doing this distinction?
I think Pitts takes those debates to be distinct as well as
because
I do.
There is a previous paper to the one you are referring to. You surely know it, on the Anderson-Friedman program about absolute objects.
Right. Yeah. Yeah.
So.
But I think, as far as I recall, that's the 2006 paper from Studies, right? So
apparently he's referring to that program, but so
yeah.
this was my.
But that's I think what he's doing there is taking general relativity and asking, does general relativity have an absolute object in it? And as far as I recall, he doesn't really say much about geometric versus non-geometric objects there. Of course, he's interested in that debate as well, and you've got this 2010 paper, which I've referenced heavily, where he talks about that. But I think he's just interested in two separate but related things.
Isn't that a different sense of absolute as well? That's like absolute versus dynamical in that earlier work, right?
Well, yeah, there's questions about what absolute really means. You could go on forever, so...
Okay.
I literally have a book contract about this.
Right, and on that note, please join me in thanking James.